Alright, the thing to keep in mind with this homework assignment is that the potential energy stored in an elastic substance such as a spring, hence the S, is equal to 1/2 of a value called K, which is the spring constant, times the stretch of the spring, how much is stretched or compressed, squared. And you notice this looks a lot like D equals 1/2 AT squared or K equals 1/2 MV squared. So it's a fairly similar setup for an equation. The one thing that's different is K. K is the spring constant, and it's basically a measure of how many newtons it takes to stretch or compress the spring by a meter. And so the spring constant is related to the force on the spring by this equation here. The spring force equals Kx. So in a sense, it's just the slope of the line where this is y and this is x. So let's take a look at this first one. The graph above shows the change in force for a spring as it is compressed 23 centimeters from its equilibrium point. Now we've got to be careful here because this is in centimeters, and when we use the values for K are always in newtons per meter. So we're going to have to convert this value here into meters. So that's the same thing as saying 0.23 meters. So let's look at A. A says determine the spring constant for the spring. So we're going to use this equation here to do that. So what we're going to do is we're just going to pick a point along this line. I'm looking for an intersection, so I chose this here because it's a nice easy intersection. If I look here, that's equal to 11 newtons, and notice I made the classic blunder. I looked down here and I said, aha, it's 1.5. I thought, wait a second, no, that's centimeters. I have to convert it to meters by moving the decimal 2 places because there's 100 centimeters in a meter. And so I had to change it to 0.015 meters. So what I have then is 11 newtons divided by 0.015 meters gives me a spring constant of 733 newtons per meter. Notice this is newtons, this is meters, and so therefore this slope is the spring constant in newtons per meter, right there. How much work was done in compressing the spring 23 centimeters? So I solved it using the area under the curve. So I said, well, if I go to here, that's it looks like it's 17 newtons. And then this is from here to here is 23 or 0.023 meters, and this area then I have to take half of it, so 1/2 of 17 times 0.03 gives me 0.196 joules. Now there's another way I could solve it using this equation here, and we'll do it in a minute. We'll get something very close but not quite the same because of rounding differences. But so it's fine if you wanted to use it this way. You could still solve for this, taking 1/2 of K and multiplying by the square of this value, well actually this value here. So let's try C. If you want to compress the spring another 23 centimeters, so what that really means is I'm compressing it 43 centimeters, which is the same thing as saying 0.43 meters. So what I'm going to do then is I'm going to use the spring potential energy equation, and I'm going to say US equals 1/2 of K times the total displacement squared. But then I'm going to take away the amount of energy that it took to displace the first 23, because the question is how much more work. So I'm going to take away this many joules from this many joules, and that gives me 0.58 joules. And then let's see, D says use Hooke's law to calculate how far the spring would be compressed if you place a 35 kilogram object on it. I'm assuming it's hanging down, and therefore the 35 kilograms would equate to an mg of 35 newtons. So I have 35 newtons hanging down, the spring is pulling up. So I'll use this equation here. The spring force equals Kx. The spring force would have to lift up with 35 newtons, which I'll put here. K is 733. I'll solve for x, and what I find is I get 0.0477 meters, or 4.77 centimeters. The data below, let's see what we got below here. Okay, this is a classic type of lab. There's every reason to expect to see this on the AP test. The AP writers love Hooke's law. it's such a nice linear nice linear relationship. I don't know, they like it. So the data as I presented to you was mass in grams and displacement in centimeters. So you had to be careful because you don't want to use grams or centimeters. You really want to use newtons and meters. So I went ahead and made two other columns. One where I converted mass to newtons. 100 grams is the same as 0.1 kilograms, which equals 1 newton. So this is really 1, 2, 3, 4, and 5 newtons. And I move the decimal 2 places for each of these and get these values here in meters, which I'll then plot on this graph here. And you see my data points do this. And they don't make a perfect line because data is never perfect, but I plotted the data as best I could, and then I drew a best fit line using a ruler. And then I'm going to find the value for the spring constant is simply the slope of the line. So I chose a point along here where I felt that I had a really good intersection. I chose 2.5 newtons because if you look at 2.5 newtons, there's a really nice intersection there. So I don't have to do any interpolation. I'm going to say 2.5 newtons divided by 0.4 meters, and that gives me a spring constant of 0.625 newtons per meter. Alright, which graph below best represents the relationship between elastic potential energy? Let's be careful. Here's elastic potential energy stored in a rubber band and the elongation, which is the value of x. So you notice x is a squared function. So if I double x, this value for the amount of energy is going to go up by the square of that. And that gives me a relationship like this. X, when you square, y is equal to the square of x. So I'm going to vote for this one right here. Number 4, the diagram above shows a 3 kilogram cart traveling at 7 meters per second. Traveling this way towards this spring. The spring constant is 500 newtons per meter. How far, so I'm looking for x, how far will the spring be compressed when the cart comes to a rest? Well, what I have to do is I have to first figure out what is the kinetic energy of the cart, because ultimately what's going to happen is the kinetic energy of this cart is going to be converted into the spring potential energy of the spring, the elastic potential energy of the spring. So my first step was to figure out, well, just how much energy is in here. So I said the kinetic energy equals 1/2 the mass, which is 3, times the square of the velocity. That gives me 73.5 joules. That's how much energy is going to be stored in this spring once this comes to a stop. Because when this comes to a stop, it has no kinetic energy, so therefore 73.5 joules of energy must be loaded into the spring. And therefore I can calculate that using this equation here. So I'm going to use US equals 1/2 kx squared. For the potential energy in the spring, I'm going to use the kinetic energy of the cart, 73.5 joules, equals 1/2 of k, which is 500, sorry I wrote it so small, x squared. Now that means what I'm going to have to do is, I'm going to say 73.5 divided by 250, and then I have to take the square root of it because x is squared. I got to get x by itself, and when I do, I get 0.54 meters or 54 centimeters. Now the next question is, how fast will the cart be going? So I'm looking for velocity now. When the spring has been compressed 10 centimeters. Well, 10 centimeters is the same thing as 0.1 meter. So what I'm going to do then is I'm going to take that and I'm going to put it into this equation here to see how much energy the cart will have transferred to the spring at that point. Because as the cart transfers energy to the spring, in other words, as the spring gains the energy, the cart loses it. And when the cart loses energy, kinetic energy, it slows down. So what I'm going to do is I'm going to figure out how much energy was put into the spring in compressing it 0.1 meters. So I take the elastic potential energy equation. For this spring, I'm going to say US equals 1/2 500 times 0.1 meters squared. And that gives me a whopping 2.5 joules. So when this spring is compressed 10 centimeters, this cart here has lost 2.5 joules. Well, it had 73.5 to begin with. So what I did then is I said the kinetic energy of the cart is equal to 73.5 joules minus the 2.5 joules that it just transferred to the spring by compressing it, which leaves me with 71 joules of kinetic energy still in the cart. Well, if the cart has 71 joules of kinetic energy, how fast is it going? Well, I'm going to use the equation K equals 1/2 mv squared and solve for v. So in this case, the K is what's left over when I take away the spring's energy, which is 71 joules, equals 1/2 of its mass, which is 3 kilograms, and V squared. So again, I'm going to basically say 71 divided by 1.5, and then I have to take the square root of it to get V by itself. And what I get is V equals 6.8 meters per second. But when I scanned it, my meters per second didn't scan because I was right on the edge of the paper there. Well, we're almost done. Let's see what we got now. I've got a pop-up toy, and I want to calculate what is the potential energy stored in the compressed spring. So I'm going to use the spring potential energy equation. The spring potential energy equals 1/2 the spring constant, which is right here, which is 150, times x squared, where x is the distance it's compressed, 5 centimeters or 0.05 meters squared, and that gives me 0.19 joules of energy stored in the pop-up toy. So when the toy is activated, it's going to convert this energy into another form. In this case, it's going to move in a vertical direction. So if it goes to a vertical height, it's gaining gravitational potential energy. Now the equation for gravitational potential energy, UG, is mg delta y. The mass times the force of gravity times the distance upwards. So what I'm going to say then is, I know that this much energy is present in the spring. We're going to assume it all gets converted to gravitational potential energy. So where it says UG, I'm going to substitute that with 0.19 joules. The mg of the toy, so let's look at the toy is, where's my toy? It's 0.02 kilograms, so when I multiply that by 10, because it's mg, I screwed up. Look what I did. Oh no, there it is. I say I'm multiplying it by 10. And I didn't screw up. I just put m, I put g, and I put delta y. Oh, good job, Eric. You didn't screw up after all. And then when I solve for delta y, what I get is 0.95 meters. It goes a little bit less than a meter, which seems reasonable for a pop-up toy. Now I'll try 6. An unstretched spring has a length of 10 centimeters. I place a 1.6 kilogram mass as hung on it, and the spring stretches to 28 centimeters. I want to know what the spring constant is. Well, what I really need to know is how much did the spring change its length. Yeah, it ended up 28, but it started at 10, so really it changed 18 centimeters. But I don't want to use centimeters, remember, because for spring constants I want them in newtons per meter. It's kind of a pain, but I had to convert it to a meter, so it's 0.18 meters. And then I also have to say, well, I can't use kilograms, I need newtons, so I'm going to take that kilograms, I'm going to find the mg of it, so 1.6 kilograms gives me an mg, a weight of 16 newtons. So now I just have to say, you know what? 16 newtons stretches it 0.18 meters, so therefore the spring constant is 88.9 newtons per meters. And I think our last one here, is it? Yes, our last one is, alright, we have a spring with spring constant of 4 newtons per meter. It's compressed with a force of 1.2 newtons. How much elastic potential energy is stored in the spring? So in order to solve that, I have to use this equation here. So the elastic potential energy equals half the spring constant times x squared. Don't know what x is yet, so I'm going to figure that out. The way I'm going to figure out what x is I'm going to go ahead and use the value that the spring constant equals the force. You know what? Why did I do it that way? I could have just done this way. I could have just said the force of the spring equals k times x, and I know that this here is 1.2 newtons, and I know that k is 4, so I basically end up with 1.2 divided by 4, which gives me 0.3 meters. So now that I know how much it's stretched, I take the 0.3 meters and I put it up here for x. I have to remember to square it. So now I have the spring potential energy equals half the spring constant k times the distance stretched squared, and when I solve it I get 0.18 joules.